Swayam Prabha. Digital India. Educated India.
In previous lectures, we have seen various kind of instability in the rotor system. Today, we will take up another instability system, especially this is occurs for a case of heavy rotors in which the gravity effect is more, and this is called secondary critical speed or the subcritical speed. As the name implies, we have resonance conditions at half the critical speed of the rotor system, and we will see that through detailed analytical expression how we can able to analyze this particular phenomena. Basically, this particular phenomena we will see that is a nonlinear in nature, and we will try to get the analytical expressions by linearizing them, and then maybe by improving the linearized solution we will try to get this particular solution. Apart from this, we will take up a case study for fluid film bearing mounted rotor. In this particular case, we will be taking a relatively bigger system, and we will try to see how a Campbell diagram can help in finding the instability of the rotor system. In the previous lectures, we have seen that with very simple rotor model, either a 2 degree of model or 3 degree of freedom model, we try to analyze various phenomena by introducing this kind of instability causes like material damping or unequal mass moment of inertia of the shaft. This kind of parameter we introduce and try to get some kind of analytical relations, so that we can able to interpret the results better way. With that as background, and we will try to see for a bigger system how we can able to get the instability directly by looking at to the eigenvalue of the system, in which in more general case, when we are considering the damping and other effect, we expect the real part and imaginary part of the eigenvalue, and we will see that by plotting them as a Campbell diagram, how we can able to find the instability into the system. So, in this model, basically prime focus will be on the subcritical whirl in rotor system due to gravity. Apart from that, as I told, I will take up one case study, because this lecture will be concluding the instability of the system. So, for a bigger system, how we can able to apply the more powerful the eigenvalue problem solution technique, by which we can able to get the Campbell diagram for finding the stability of the system. And in this some new terminology like subcritical speed of whirl, and as I mentioned, this equation of motion for such phenomena will be nonlinear, and through some linearizing method we will try to solve this equation. So, regarding the secondary or subcritical resonance phenomena, Stodula in 1924 initiated theoretical analysis and experimental studies on this particular phenomena, and he basically considered a Jeffcott rotor. So, I will explain this by a simple Jeffcott rotor. So, in this we have one Jeffcott rotor like this, where this is the disc. This is mounted on some rigid bearing, maybe rolling element bearing. So, flexibility of the bearing we are not considering. Apart from this, so here we can able to take this is the undeformed. So, this is the bearing axis, and our axis system origin is here, and let us take this as axis system, in which let us say horizontal axis is x, this is y, and accordingly we have z direction, this one, and in this rotor is rotating with let us say nominal speed of omega. In this is the center of the disc. Eccentricity of the disc could be somewhere here. Let us say this. I have exaggerated the location of the center of gravity. This is the mass of the disc, and now let us try to draw the free body diagram of this particular disc separately, so that we can able to see various forces which are coming onto this. So, we have this is the axis system, which is stationary rotating axis system. Let us say this is the disc, this is the bearing center line point, and this is the center of rotation of the disc. Because we removed the disc from the shaft, we expect elastic force will come. So, this is because this distance is k, this is y. So, we will be having ky and kx forces, which will be acting at the center of gravity, center of rotation c. Let us say center of gravity is here, g, and mg is acting down, because now the reference axis is at the bearing axis, not at the static equilibrium position, as in the previous case of run up and run down equation of motion. In that also equation of motion was nonlinear, and because of that we considered the bearing axis at the as the reference for these x and y axis. So, here also we are considering the gravity effect in this, and let us say our reference for the angle measurement is x axis. So, this is the theta. So, this is the direction of rotation of the disc, which is theta dot angular velocity. So, in this case also we do not have the angular velocity theta dot is not equal to nominal speed into this, but basically it varies. So, we will see how we can able to simplify this particular in the subsequent analysis. So, now various forces are we already applied onto the disc once we take the free body diagram of the disc. In this, and apart from this, if we want to analyze, we need to take rotating coordinate system, that is more convenient, as we already seen in some of the case it is more convenient, which is rotating with omega t. So, now we want to obtain first the equation of motion of this rotor in x, y and theta direction, and then we will try to analyze the rotor system. So, in equation of motion in x direction, this is the elastic force which is acting here. Apart from that, we have gravity force, and in this particular case the choice of the axis is basically in this equation of motion is in the vertical direction as positive. That is why this is negative and this is positive. So, basically In that particular case, for derivation of the equation of motion, x will be vertical, y is horizontal itself, but so like this. So, because of that is negative, otherwise there is no problem in the sign. So, this is the equation of motion. Basically, you can able to see this is the weight, and in this particular case, as we have seen in the previous lectures also, this is the position of the center of gravity of the rotor, and in this particular case, this is the linear acceleration. So, if we differentiate this, this will be having a differentiation which will come here, but differentiation of this will give us two components like this. In this E is constant, is not variable, but this will give two components like this once we differentiate twice. Similarly, in the y direction we have elastic force, and this is the mass into acceleration term, and if we simplify this, basically we will get this. Here also we will get two terms, and the third equation, which is moment equation, we are taking moment about center of gravity. So, moment about center of gravity will give moment, because these two elastic force, should be equal to the polar moment of inertia into the angular acceleration. So, basically these are the three equation of motion, and the third equation we can able to simplify like this. So, I p we can able to write it as mass into radius of gyration square. So, k 1 is the radius of gyration of the disc. So, we can able to write in that particular form. K is stiffness of the shaft. So, these two are different. Now, to analyze this particular system, first we are defining a complex displacement x as S is equal to x plus j y. So, first two equation, this equation and this equation can be combined like this. So, basically we are multiplying the second equation and adding to the first equation. So, this two term is we are getting, and then this is from the this. So, you can able to see various expressions we will be getting like this. From this we will get this. So, basically we can able to get the expression like this. So, basically we are using cos theta plus j sin theta is equal to E j theta. Now, this is the thing we are using, and wherever there is a problem in the something like this sin theta plus j cos theta, this kind of terms are there, then we are converting this into this form, and by taking some common to j, and because of that these terms we are getting. So, basically this is the equation of motion in complex domain, but stationary coordinate system. We want to convert this into rotating coordinate system. For that we already developed in the previous lectures the transformation. So, this is the transformation in which zeta is the complex displacement in rotating coordinate system, and this is in the stationary coordinate system. These two coordinate system we already seen that they are rotating with respect to each other with omega, and if we use this here, we have already done earlier this several time, this double dot, this kind of transformation. So, if we take derivative of this first, second and substitute in this equation of motion, basically we will get equation like this, where some terms even we will get with xi dot also. This is not damping term, but because of the differentiation which we do, because of that we are getting these terms, and these equations will also get transformed. Now, you can able to see this gravity force, which is in stationary coordinate system, is a constant force. In rotating coordinate system, it will appear as rotating in the opposite direction, because if person is sitting in the rotating coordinate system and if he is observing the static force which is there in x direction, it will appear to him as it is rotating in the opposite direction of the axis on which it is sitting. Similarly, here there will be difference in the frequency because of the observer will be sitting onto the rotating coordinate system. So, that much difference will come in the. So, this will come directly from the transformation. And the third equation, the moment equation which we had here. So, basically we will see that this particular term within the bracket is nothing but nu. So, the nu and xi are basically two axes which we have chosen, which is a rotating coordinate system. So, this is in the previous lecture we already seen this relations. So, that will be nu, other terms are same. So, basically this equation and this equation is the nonlinear equation. Now, you can able to see because some of the terms are having square. So, this is a nonlinear equation of motion and is in the rotating coordinate system. Now, first we want to obtain the unbalanced response of that particular equation of motion, and theta, which is angular displacement of the disk, which is the theta dot is not equal to the constant angular velocity. So, what we are assuming here that that is equal to omega t plus some small quantity which is time dependent, and this u dot is time dependent deviations of the angular velocity. So, time because this is a nominal speed, and whatever the variation is taking place of that speed is there in this. So, basically u is nothing but the angle, the torsional displacement, torsional angular displacement. So, and as an initial approximation to solve the previous equation, we are assuming that this torsional displacement is negligible, and we are saying theta is equal to omega t. And with this this condition we are substituting in the previous equation of motion here, theta is equal to omega t. So, basically this equation will become the linear equation. Right hand side will take a simple form of like this, and so this is in the rotating coordinate system complex or displacement equation. Right hand side is now a known quantity, theta is now vanished because we have chosen this approximation. So, with this we can able to now, this is a linear equation now, this we can able to solve it. We have one in rotating coordinate system, we have one constant force, another is time dependent force. So, we can able to choose solution for this and this separately, because it is a linear system. We can able to obtain the solution of these two independently, and then we can able to superpose these two solution. So, first solution is corresponding to this constant term. Let us say zeta is equal to a constant term, a we need to obtain. So, if we substitute this in this equation of motion by not considering this one, so we will see that this term will be 0 because it is a constant, this will be 0. So, this will give a is equal to this divided by this quantity. So, e omega square by this quantity. So, this will be the a corresponding to this. This is the amplitude of the solution corresponding to this constant term in this. Similarly, for solution of this we can able to choose some constant and this frequency. So, e minus j omega t. If we derivate this twice, substitute in this equation by neglecting this one, we will see that b. So, basically we need to take the derivative of this. So, that will give minus j omega b e minus j omega t, double derivative that will give that is omega square b e j omega t, and these 3 we can able to substitute here, and then we can solve for b, because b is the quantity which will be obtaining. So, we will see that b will get simplified to this simple expression of b is equal to g by this quantity. So, now we can able to write the solution for this, the simplified equation, linearized equation like this. So, this is the constant term and this is the b term. So, this is the solution of the previous equation. In this omega nf we are defined as undamped natural frequency. We can able to take the real part and imaginary part of this separately, because in the third equation, this equation we have eta. So, we want to substitute this assumed solution here, and whatever the solution we obtain we want to substitute here and then solve for theta. So, basically we can able to separate this in real part and imaginary part, because imaginary part is having this is only real part. So, this constant term will not come in this. So, this eta now we want to use in the third equation to get the theta variation. So, now you can able to see if we substitute. So, now as a second approximation. So, that means now we want the updated solution. For that we are again now introducing theta is equal to omega t plus u t, and this we are substituting in the third equation, and that requires theta double dot. So, theta double dot you can see this will vanish, this will give us u double dot t, and this we are substituting and this in the moment equation, this moment equation. So, basically with this we are trying to get what is the variation u t. So, we have substituted eta from here. So, now this we can able to solve for u, and the solution will be something like u is equal to some constant sin omega t, and if we differentiate this twice and substitute in this equation, we can able to solve for capital U, and basically this will be the capital U within the bracket term. So, this is the solution of this equation of motion, and now with the third equation we can able to see that we could able to get the what is the variation of the theta. So, in the first approximation we assume this is equal to 0, we got the value of the xi and eta. That solution which was approximate we used in the third equation to get the variation u, and now we have variation of u. So, now this solution we can able to substitute in the theta expression, and again we can go to the equation, this equation in which the theta variations are there, because we need the more accurate solution of this. The first solution which we obtained by considering the angular velocity as constant, but now again once we obtain the variation of the angular displacement, we want to use this expression here. So, this theta now will be substituting in the right hand side of that equation. So, basically theta is now defined like this. So, if we take derivatives of this double derivative, because that contains some square terms also and some other terms. So, they can be simplified. In this you can able to see this, because u is very small variation. So, some kind of approximations we will be using it wherever we are getting some kind of nonlinear terms. We will try to substitute drop those nonlinear terms. So, basically if we substitute the theta is equal to u omega t plus u in the equation of motion, we will see that in the right hand side this term basically will give this, which will give this simple expression. So, basically equation of motion will be having this form. So, this additional term which will be getting this, and this was already there in the previous expression when we linearize the equation of motion. So, if we go back to this equation of motion, which we linearized it by putting theta is equal to omega t, we had these two terms. Now, with this variation, we are getting a additional third term, or this term, and this term you can able to see it contains the gravity terms also, apart from the other parameter, but this is the main parameter. So, now we want to solve this particular equation. For solving this again, because now with this equation is linear again, we can able to solve for this and this force separately, and we can add it. We already solved for this and this in the previous expression. Now, we will be solving for this, and we will see that the solution of this for all three will be like this. So, basically this is the additional term which we are getting, which was not there in the previous solution. So, in the previous solution only two terms were there like this only two terms were there. Now, we are getting a third term because of the variation in the theta. So, now if you look into these equations, so better we can able to transform this in the stationary coordinate system, because now the solution is in the rotating coordinate system. So, if we transform this in the stationary coordinate system, we will see that basically here whatever the transformation we had earlier, this transformation now it will be opposite. So, to transform back into the original system, we need to use minus of omega t. So, this transformation we need to use to transfer this in the. So, basically that will get multiplied by the j omega t. So, basically this is the complex displacement in stationary coordinate system. So, if you see this equation, this term, this is the deformation of the shaft due to gravity, because there is no time dependent thing. So, this is static force. So, whatever the gravity force is there, because of that this much deformation will take place. On the first term, this is the amplitude. The frequency of this particular response will be equal to the spin speed of the shaft. Frequency is equal to spin speed of the shaft, and in this we are getting a condition that when the frequency of the shaft is equal to undamped natural frequency of the shaft, we have resonance condition. So, this is standard due to the unbalance, because this E is there. So, this response is purely due to unbalance, in which we know that there is a resonance whenever the speed is equal to the the undamped natural frequency of the system, and the Whirl frequency for unbalance we know is equal to the spin speed. So, this is also we know from the previous analysis. Now, coming to this term, in this if we say this frequency component, we have frequency of the Whirl corresponding to this is twice the spin speed. So, frequency is twice the spin speed, and as I mentioned earlier, here this is due to the gravity. Mainly this particular phenomena is coming. If there is no gravity effect, then this whole term will vanish, and in combination with that there is a, because of the eccentric application of the gravity. So, if E is also 0, then also it will not be 0. So, basically this particular phenomena is combination of the gravity effect and when gravity is acting eccentrically to the rotor system, which is always present, E is always present as we know in practical rotors. So, the Whirl frequency is twice the spin speed, and if we see this denominator here, so from here we can able to see that there will be resonance when the speed is half the natural frequency. So, when omega is equal to half the omega nf, then the resonance will take place. So, the resonance is taking place when the speed is half the undamped natural frequency, which is quite different as compared to this particular case. In this particular case, when the speed is equal to the natural frequency, then we have resonance, but here when the speed is half the natural frequency, then the resonance is taking place. But the frequency of whirl is twice the speed of the shaft. So, this we need to observe carefully, that the resonance is at the half the critical speed. That is why it is called secondary or the subcritical speed, because when the speed is below the critical speed, then also this resonance is taking place, but the whirling frequency of that is twice the natural frequency. That means, at resonance condition, when we are operating at this, the resonance will take place and the frequency of whirl will be twice of this, that means equal to the natural frequency. So, this is very interesting phenomena of the subcritical speed, in which the resonance is taking place at half this critical speed or the natural frequency, but whirl frequency is at the natural frequency. So, this is we have explained here. So, this is static deflection, this is unbalance, this is eccentric application of the gravity. Because of that, this secondary resonance phenomena is taking place. So, this I have already explained in detail how this particular phenomena is taking place and what is the amplitude of that particular phenomena. And commonly we know that gravity and the unbalance the response is well known, but the secondary resonance phenomena is not quite well known in literature, but it has been explained quite early in 1924 by Skodala. Now, we will take up a case study in which we will be taking a slightly bigger system and will try to demonstrate that through finite element method, which is more versatile method for modeling any rotor system, either is a 2 bearing or multiple bearing support system. Finite element method we already seen that is very conveniently we can able to model a rotor system. Even in that we have seen that the bearing can be added quite conveniently, or gyroscopic effect we can able to analyze. So, in this particular case we will try to analyze a rotor system and we will try to see how we can this particular rotor will be mounted on fluid film bearing with all the 8 linearized coefficients of the stiffness and damping, and with that we will try to obtain the whirl frequency of the this particular rotor system. In this not only we will be considering the bearing as 8 linearized, but will in the second case study we will be considering the speed dependency of these particular bearing property, because in the previous lectures we already seen that especially fluid film bearing, they can have some kind of when the speed changes, their static equilibrium changes, and because of that the property of these bearings, stiffness and damping, changes with speed. So, using short bearing approximation we will try to incorporate that particular speed dependency in the rotor system and will obtain the Campbell diagram. In the Campbell diagram, apart from the frequency, we will put the logarithmic decrement also, that will give the idea about the stability of the system at various speed ranges. So, there is another way of finding the stability of the system, especially for the complex system. So, in this particular case we are taking basically a rotor system like this. So, there is a huge rotor with 4 discs are there, they are also heavy discs. These bearings are fluid film bearings, and we will be modeling this particular rotor system using a finite element method. And various property of the rotor and bearings are given here. So, basically here we want to demonstrate the application of the finite element method for typically simply supported rotor disc system. But this boundary condition is not a limitation for finite element method, as we know. Various physical property of the rotor system is like shaft diameter is 0.1 meter, length of the shaft is 3.5 meter, material properties are given here, Young's modulus and density, Poisson's ratio. Number of discs are 4 as we have seen in the figure, and they are very heavy disc 60.3 kgs each of them. Both the bearing are linearized, they are idealized as identical fluid film bearing, and their L by D ratio is 0.5, which we can able to consider as short bearing. We need to consider 2 cases. One is the speed independent bearing characteristic. In this we are choosing one bearing parameter, and we will keep constant that during the change of the speed. And in this particular case another is the speed dependent bearing characteristic, in which we will be varying the speed of the property of the bearing with the speed. So, we can able to this is the in this particular case just to show the convergence, we have taken 2 cases. One is we have idealized this as 7 element, and in this second case we have considered that as 14 elements. So, we have divided this various shaft segments into 2, so that the number of element becomes 14. So, for speed independent bearing characteristic, various parameter of the bearing like D, L, where L by D is this, radial clearance, viscosity at the operating temperature we have provided. So, direct as well as the cross coupled stiffness and damping coefficients we can able to find for any particular speed. So, what we have done at 4000 RPM we obtain the bearing property, and we are assuming that that remains constant for all other speed. So, something like average speed we have chosen. So, these are the by short bearing approximation which we described earlier for is mean speed of 4000 RPM and various bearing property we can able bearing parameter we can able to get the stiffness coefficients and damping coefficients of the bearing like this. Now, in this particular case, because I am not describing the detail of the FEM formulation that we already discussed in detail earlier. So, directly I am giving the Whirl frequency, because so here you can able to see one is the 0 speed. So, at 0 speed we have basically this is a nearly 0 speed, this is not 0 speed. So, that is why you can able to see there is a slight splitting of the frequencies are there. So, this is very low speed, basically this is not 0, at very low speed 1 or 10 radians per second was there, and we found a slight splitting of the natural frequency at this. So, forward and backward fold, and these are the logarithmic decrement. So, basically in the eigenvalue as we described earlier, this beta gives the Whirl frequency and alpha is the damping parameter, and with alpha we define the logarithmic decrement, and whenever this logarithmic decrement is basically positive or negative, we have instability. So, you can able to see that in this particular case, when speed is low, we have stable. So, in this particular case, the logarithmic decrement has been defined. When they are negative, the instability is there. So, you can able to see that in this particular case, as we are increasing the speed, the splitting is more in various. So, these are the first four Whirl frequencies, first four because they are changing in the speed because of the gyroscopic effect in the disk. So, these are the at various speeds. So, basically you can able to at various speeds we obtain these first four Whirl frequencies and their logarithmic decrement, and these can be plotted in a Campbell diagram. So, this is the speed and this is the natural Whirl frequency. So, you can able to see at low speed, because in this we are considering the gyroscopic effect. Because of that, the splitting of the natural frequency is taking place as the speed is increasing, and these are the upper one is the forward Whirl and lower one is the backward Whirl. So, wherever the negative logarithmic decrements are there, they are unstable regions of, and in this particular case, this line is the speed is equal to Whirl frequency line, and these are the critical speeds. So, the forward critical speeds have been shown here. So, in the third natural frequency, the splitting is not much. This is the fourth. So, these are the forward critical speeds and the lower one is the backward critical speeds. So, in this you can able to see the logarithmic decrement is defined both for the forward and backward. So, as such the backward Whirls are stable, here they are unstable. So, here also they are stable, here it is unstable, but if you are going to the higher one, this third mode is stable because this logarithmic decrement is positive, here also is stable. So, in this particular case at lower speeds, the first forward and backward Whirls at low and high both they are unstable, but at the higher modes are stable, lower modes are unstable, but higher modes are stable. So, this is one of the Campbell diagram. Critical speed and logarithmic decrement of a rotor system supported on speed independent bearing. So, basically previous tables was for the Whirl frequency, now this is for the critical speed, the intersection of the 45 degree line. So, here that summary we are giving. So, basically, and in this we have given for 7 element and 14 element what was the difference in forward critical speed and backward critical speed, and this is using some kind of condensation scheme or static condensation scheme, how the result affects. So, basically in this all the rotational degree of freedom we eliminated, and we saw the effect of the. So, not much effect we observed, especially at the low frequency lower modes this particular condensation scheme, but higher frequency because it is static condensation we expect more error for high frequencies. So, in this you can able to see these are the critical speed forward, backward, and these are the logarithmic decrement corresponding to that. Second mode, this is forward critical speed, backward critical speed, this is with the more number of elements. So, we expect these will be more accurate as compared to these ones, but up to second mode I think we are getting quite close values. So, this is the summary of the Campbell diagram, critical speeds and their logarithmic decrement. Okay. So, this is the comparison of the critical speed just for we want to compare the same rotor if it is mounted on some kind of rigid bearing or simply supported bearing, what will be the difference that we wanted to see. So, you can able to see that critical speed with rigid bearing and with fluid film bearing. So, obviously, we expect with fluid film bearing there will be decrease in the natural frequency or critical speed. So, we could able to observe that especially at higher modes the decrease is more, the critical speed decrease is more when we are comparing with the rigid bearing and the fluid film bearing. So, you can able to see that if we consider the fluid film bearing as rigid, how much error we can enable to incorporate in the calculation, especially for the higher modes. So, this is very interesting comparison between the rigid bearing and the fluid film bearing model. So, obviously, this model is more accurate, and if we consider the fluid film bearing as simply support, then we may get erroneous results, and especially here higher modes you can get error of maybe 26%. That is a typical result, but is not valid for all cases. Then next we will be considering the speed dependent bearing characteristic. In this, direct as well as the cross coupled stiffness and damping coefficients are considered as speed dependent. These are calculated based on the short bearing approximation expression as function of speed. So, here these are the same bearing parameter. Now, we are calculating the stiffness and damping parameter as variation of the they are varying with the speed. So, when we discussed this particular short bearing approximation in previous lectures, so because they were in the non-dimensional form. So, for this particular bearing we can able to get those parameter, and we know that they vary with speed. So, those values we have directly fed into the our programs. So, this is the Campbell diagram when the Whirl frequency map of rotor bearing system supported on speed dependent fluid bearings are considered. So, here you can able to see the similar 1, 2, we have considered up to 4th mode, and we have given even the logarithmic decrement of this. So, you can able to see that especially the lower modes are unstable, but higher modes are unstable at very high values of the speed. So, this is the same values of the Whirl frequency. In some cases, we are not getting these values because whatever the model we consider, here we are not getting the natural frequency, because in previously we already seen that some cases if we are in the unstable zone, we may not get the these frequency, or sometime because of the gyroscopic effect, especially the suppression of this kind of frequency critical speed occurs. So, these are the variation of the Whirl frequencies which we have plotted earlier, and also the logarithmic decrement. And this is the summary of the critical speed and the logarithmic decrement for speed dependent bearings. So, for 7 element, 14 element, and with condensation of the some intermediate support and the angular displacements. So, basically you can able to see some of the modes are stable, or whenever negative logarithmic decrements are there, those critical speeds are unstable, like this one. Today we initially started with the subcritical resonance phenomena or secondary resonance phenomena. We have seen that in that particular phenomena that take place because of the eccentric application of the gravity, and in this particular case we saw that not only the response due to the weight of the rotor, which will be something like static deflection will be there in the response, we will be having even response of the unbalance, because eccentricity is always there in the rotor system. Apart from that, we got a secondary resonance amplitude. Those amplitudes we saw that in that the resonance take place at half the undamped natural frequency of the system, and but the whirling frequency at which the rotor take place at this is twice the speed of the rotor. That means at the critical at the natural frequency of the system. So, that is the very interesting phenomena which we observed, that is due to the eccentric application of the gravity. Apart from that, then we try to apply the finite element method in more general case, in which we consider the gyroscopic effect. The bearing property we considered as speed as a fluid film bearing. In that two cases we considered, that is speed independent and speed dependent bearing property. With that, how the system stability we can able to obtain, we try to find out using the logarithmic decrement. So, with this we can able to see that even a bigger system by finite element method we can able to find the instability of the rotor system. In the subsequent lecture, now we will go for more practical application of various methods, like especially various kind of faults are there in the rotor system, how they can be identified or how they can be rectified. So, we will begin with balancing of rotors, not only the rigid rotor, but also the flexible rotor balancing theory we will study, and with some numerical example we will try to understand those methods in more detail.